So welcome to this last seminar regarding characterization and properties of quantum channels. So we went through 3 seminars about, first of all, deriving the Gorini, Kossakowski, Sudarshan, Lindblad master equation, talked about dynamical semigroups, and so on. In the second lecture, we talked about all the different ways that you can represent the CPTP maps. So this lecture is about how to go from the master equation to the CPTP map. In particular, how you can go from the master equation to the Kraus operators, okay? I could only find one reference about this procedure, and it's this paper, this famous paper by Erika Andersen in Journal of Modern Optics. The thing is that the paper, given the notation that we've been using and so on, it might be a little bit difficult to read. So I've tried to basically just make the procedure as simple as possible. Okay, and in fact, the procedure is very simple. It only consists of essentially 3 steps. The first one is, if you're given the Gorini, Kossakowski, Sudarshan, Lindblad generator, you construct a matrix representation of this generator. Once you have this one, you can construct a matrix representation of the corresponding map simply by doing this. This can be done numerically. Normally, this is just in general. This matrix here, you can always put it in Jordan form, and then you can take the exponential of it. And once you have this, the third step is to construct the Choi-Jamiolkowski. So we're going to use this matrix to go to this matrix. And once you have this matrix, you diagonalize to obtain the eigenvalues and the eigenvectors. And then from the eigenvectors, you obtain the Krauses, okay? Essentially, this is the procedure. Okay, so I'll walk you through exactly how to do these 3 steps. So first of all, let's remind ourselves that what the dynamical generator looks like, right? So we said that here you put whatever object. There is the unitary part, which consists of a Hamiltonian. And then if you remember, we had this, I'm assuming here that the Hilbert space is n-dimensional. We had this Gorini, Kossakowski, Sudarshan, Lindblad matrix C, which has to be positive definite. And here we had our GK.GL plus GL, right? Where these GKs form an orthonormal basis of Hermitian operators for the Banach space. Okay, so let me just make this explicit. You don't have to use these bases. You can use any basis, but it is always convenient to use this Hermitian operator basis, okay? For many reasons. And if you remember, I think last time I called the last element the identity. This time I'm going to call the 0th element of this basis. I'm going to normalize the identity for this, okay? So how do we obtain the matrix representation? Very simple. If you remember, the matrix representation of any CPTP map T, so has elements KL that are given by the trace Okay? And if we plug in since this is a dynamical semigroup generated by our Gorini, Kossakowski, Sudarshan, Lindblad, this is this. Okay? If you expand the exponential in the Taylor series, okay, then what you will get is t times the application of the Lindblad on this GKL to many powers, but this, which means that the only thing you need here is that this the matrix representation of E of t is simply E to the t, the matrix representation of L. Okay? And this, just to make it more explicit, so here we have, these elements are just the trace, GK, apply the generator on GL. Okay? So again, very trivially, you just write the exponential here in its infinite Taylor series, and what you will get is the application of L on this, take the trace with that, but that's the matrix representation. So at the end, what this thing is telling you is that the matrix representation of this is just the exponential of the matrix representation of the other thing, okay? Good. This we know how to do. Essentially, we just apply every element of this basis. We put it here. We calculate the outcome. We take the trace with another element of the basis, and this fills out the matrix representation. Okay? The tricky part is to go to step 3. So this is 1 and 2, actually. Okay? Now, how to do that? First of all, remember that the Choi-Jamiolkowski representation, I'm putting a hat because I'm going to be using the physicist definition. You don't have to. If you don't put a hat, actually, it's a little bit simpler, but let me just do it for the sake of, since we're all physicists here. This is the definition, where this phi plus state is the maximally entangled state. Remember, I'm assuming that the underlying Hilbert space is n-dimensional. Okay? Again, a reminder, you can switch the order here if you want, so you can apply them up on the second register. I normally apply it on the first one because you see, for a reason, if you do this, we're going to be using these vectorization identities. Having the channel on the first register makes the vectorization a little bit simpler to do, okay? We don't have to take transposes and all these things, okay? Now, if we plug this in here and expand it out, right? What we will get is the following form. Okay? And if you remember, this is yet another orthonormal basis for the Banach space of operators, but it's not necessarily this basis, okay? So let me then define a new basis. Okay. So alpha is a multi-index, okay? I'm using one letter to define both I and j here, okay? So I'll define another basis of operators fa, okay? So instead of writing here ij, I just write alpha because we're gonna need to sum over alpha and I don't wanna write ij all the time, okay? Notice that this is a non-Hermitian orthonormal basis for the bounded operators on H. Okay? So that we can write more succinctly this guy as sum over alpha, E of f alpha, tensor of alpha, okay? The trick, really the only hard thing to do is, I have the matrix representation of E, but I have it with respect to this basis. And here, I have the application of the map with respect to another basis. So all I need to do is express this operator in terms of my other basis, right? And take the trace with respect to that other basis so that here I can literally plug in the matrix representation. And once you do that, you're done, okay? So let's do that. A bit of a warning. In the original paper by Anderson, what they do is they express both this register and this register in the Hermitian basis. Okay? You don't have to do that. You can only express this one and leave this other basis alone, okay? It's the same thing. The reason why they do it in Anderson is because the general output expression looks a bit more symmetric, but you don't have to, okay? So all I'm gonna do is really change the basis for this register only. I'm gonna leave this basis alone, okay? So now what we're going to do is, we're going to express first this guy with respect to the basis GK. All this says is that this thing here is equal to, have here the sum over K, the trace. Remember, these operators are Hermitian, so I do not have to put the dagger here. Agreed? Right? That's the first step. The second step is to express whatever comes inside here, because my matrix representation, right, is with respect to this basis on both sides. So I need to write FA as the sum like this. Okay. And now I simply plug everything in. So we have, I actually forgot to write it here. 1 over n. We have the sum over alpha, the sum over k. Here we have the trace of gk t of t, and inside here we have the sum over L, the trace gl f alpha gl, and close this one. We close this one, and here we have gk tensor f alpha. Okay. Now I use the linearity of quantum mechanics, so the linearity of the trace, the linearity of the operator, and so on. And I can write this expression as sum over alpha, sum over k, the trace of gk, sum over L, the trace gl f alpha, d of t on gl gk tensor f alpha. So all I did to go from this point to this point is I just moved the sum outside here, which I'm permitted to do. Next step is I'm going to move it even one step further. This is a number. I can also move that number outside. So this becomes and we have what we want, right? Because you recognize now that here, this is nothing more than the matrix representation element KL. This here is effectively a unitary transformation because this is a change of basis. Let's call this unitary UL alpha. Okay? And now I'm going to write them in, I'm going to change the order here and look at this sum. Okay? This sum is the sum over L. Remember, these are numbers, I can switch them. This says M of ET KL UL alpha. And this you recognize as the matrix element of multiplying the matrix representation of MT by this unitary U and taking the K alpha element of it. Okay. And now we are essentially done, right? Because as soon as you have this in this form, the next step is you diagonalize this operator, since the Choi-Jamiołkowski operator is positive semi-definite, right? So you perform the spectral decomposition. This means that this J of ET can be written as a sum over n. And now I'm going to use this double Kerr notation to let you know that these are vectorized forms of operators. I put a hat because these are orthonormal eigenvectors, right? So to obtain the Kraus operators, all we need to do is we take square root of n. This is because I used the physicist definition. If you don't normalize the Choi-Jamiołkowski, you don't have to do this part. Okay? I have to take the square root of lambda n, and then I have to undo the vec of this guy. Okay? And this will be my Kraus operator Kn. And that's it. It's a big anticlimax. I know 4 lectures to get to this point, but sometimes that's how the penny drops. So I have here worked out an example explicitly, but then I realized that it might take too long to actually write down. So what I did is I codified it in Mathematica, so you can see exactly all this procedure. Okay, so if you finished writing, I'll turn on the projector and then show you how to do it. Oops, no, where's the, can you turn it on? Thanks. Noelia, are you done?
Sí, sí.
Ah, vale. Excellent, okay, so okay. So here's the entire procedure codified. Okay. So first of all, I define the normalized Pauli operators. This is our G basis, and here's our non-Hermitian computational basis. So the example I'm going to do now is an example where the underlying Hilbert space is a 2-level system. Okay. And in fact, the master equation we're going to be looking at is the one that corresponds to spontaneous emission. Okay? Spontaneous emission means, maybe I'll write this one down. So here's our example. Okay, the master equation for any state rho. For this kind of noises, we have the Hamiltonian, whatever the Hamiltonian is. And here, normally, for the spontaneous emission, we have the rate, gamma. And here we have where the sigma plus minus are the raising and lowering operators, okay? So this is sigma x, okay? Now, as you may notice, this is not in the standard Gorini, Kossakowski, Sudarshan, Lindblad. We need to put here the Paulis. So what you do is you substitute for C plus minus these guys, expand it out, and you bring it into the standard form. So we can obtain the Gorini, Kossakowski, Sudarshan, Lindblad master equation. Okay, so here is me codifying it in the most general form. I can't use the letter C because that's reserved in Mathematica. So what we call CKL, the coefficients, I call them AKL. Okay. Here's a little module that, given the master equation, writes down the matrix representation of it. Okay, and this is the Gorini-Kossakowski Sudarshan matrix representation for this channel. Okay, instead of gamma, I called it X. Okay. Here, let me make this. Maybe I make this a little bit bigger. Is it worth it? Yes. Okay? Now, the first thing I'm going to do is I'm going to assume that we only have dissipative dynamics. In other words, I'm going to pick the Hamiltonian to be the identity so that this part here effectively goes away. Okay? And we're going to look at what the dynamics are. So, oops, jumped ahead here. So, here is the matrix equation of the Liouvillean. Okay? Then I just do the exponentiation. So this is my matrix M of the map. Okay? And here's a little module for constructing the Choi-Jamiolkowski. First of all, I define the unitary, which changes the basis from the computational to the Pauli's, which is this matrix here. Then remember, I have to do this multiplication here, M times U, which is what this is doing. Okay? And then I just construct the Choi, which looks like this. Notice that this is a bona fide state. In other words, it is Hermitian, and its trace is 1. Okay? Then I just find the eigenvalues and eigenvectors. Okay? You have to be very careful with Mathematica. Mathematica normally doesn't normalize the eigenvectors, so I make sure that they are normalized. Okay? And then I extract the Kraus operators exactly with the procedure I told you. In Mathematica, this vectorization is simply just a reshape of the matrices. So you basically take the vector and unstack the entries. And here are the Kraus operators. We have 2 that are 0 because our matrix has 2. Our Choi-Jamiołkowski operator has 2 0 eigenvalues. And then the 2 non-zero eigenvectors are these ones. Okay? Those of you that are familiar with quantum info will recognize this as what in quantum information parlance is known as an amplitude damping channel. Okay? So spontaneous emission corresponds to an amplitude damping channel. And generally, the amplitude damping channel has 2 Kraus operators. The first one and the second one. Okay? And you can associate X with 1 minus gamma t e to the minus gamma t over 2. Okay? So the next part is I'm defining a few matrices to determine the action of our channel to see if it makes sense. So the first thing I do is I apply the map on the ground state. If my system is on the ground state, there is no spontaneous emission. So this should be a fixed state of the channel, and indeed it is. If you apply the map, I get back the same state. Okay? Next, I look at the excited state. What happens to the excited state? Well, as you can see, I started with something which is here, and I get something which goes down here and goes up here. Okay? And I chose here, just for purposes of illustration, let's assume that the rate is 1. And as you can see, this is the ground state. So this is the excited state that goes down to 0, and the ground state that goes up to 1. Okay? And the last state I picked is something which has a superposition. Okay? Something which is on the equator of the Bloch sphere. And if you now calculate the action of the channel, you see that there is this part remains the same as before. And now we also have a damping parameter here. Okay? Sorry. This one, hold on. Let me fix that because I think I ran it for a different Hamiltonian. So let me just redo this. Here's the Choi, here's the eigenvalues, here's the eigenvectors, here are the Krauses. And now, right, now is the correct one. So if you can, so as you can see, we have the coherences also decay, but they decay quadratically slower than the populations. Okay, and let me now also fix this. And then just to show you what happens to the coherences, I'm defining these two projectors, which are in the plus minus, to basically track how the coherences decay. So if I now compute this probability and I plot it, you see the decay rates, no? So they both converge slowly, going to 1/2, which means that the state essentially is slowly going to the mixed state, okay? Now, you might be wondering, okay, what happens if I put here a Hamiltonian? So for example, in the lectures that Danny gave you, the Hamiltonian was omega 1,1, right? So let's put that Hamiltonian in. This is here. Let's make omega 10, okay? And 1,1 is our operator F4, okay? So I rerun things again. Now you see what changes is I have the omega, minus omega on the off diagonal there. This will result in me having an oscillation here, actually a damped oscillation, okay? And then if I run the Choi, and we look at the Krauses, again we get the first two Krauses are 0. The third Kraus is that one. The fourth Kraus now has a unitary part here. And now if we calculate the action on particularly this state here, right? Because in order to get the oscillations, we need to have a state that has off-diagonal elements. So if I now compute it, you see that I get this very cryptic form here. But if I were to look at the projections, oops, what happened? Oh, I forgot to do this one, yeah. Okay, and now here's the pattern that also appears in Danny's paper. So you see the oscillations between the coherences slowly dampen out, okay? So if I pick a gamma, if I pick an omega which is larger, there will be more oscillations here. If I pick a gamma that is higher, this will be overdamped. If I pick a gamma which is smaller, it will be underdamped, and there's a critical value and all these things. But you see, you can analyze it just by looking at these two Kraus operators here, okay? In fact, you can prove that so long as, so here's the Hamiltonian again. Let me remove this one. Let's call this part here is normally referred to as the dissipator, okay? So this is the unitary part and this is the dissipator part, okay? If you work out the dissipator, like we did, in other words, you put the Hamiltonian as the identity and work out the Kraus operators of the dissipator, then, let me just make sure I get the conditions right. If your Hamiltonian and your dissipator obey this equality, then the Kraus operators with the Hamiltonian are equal to U times the Kraus operators without the Hamiltonian. Okay, and this U is this. Okay? And you can check. In fact, you saw it when we did it, right? The only thing that changed in the Kraus operators, if you remember, was that before we had a 1 here, and now we have an e to the I 10it. This is because this unitary is exactly that multiplication, okay? If they do not, if the Hamiltonian doesn't satisfy this condition, okay, then you have to solve this system. You have to go through this procedure all again. You have to put it here, find the matrix representation, do the exponentiation, do the unitary basis rotation and all that, okay? And in fact, it can get very tricky. So for example, if you want, I can give you this file. Try putting here, for example, the Hamiltonian being the rotation around the x-axis. Then you'll see this at some point breaks down. In fact, even Mathematica, even though it's a 4x4 system, when you do the matrix exponentiation, it has a problem. So you have to go and manually do the Jordan decomposition, then do the exponentiation in order for Mathematica to work, okay? But in principle, you can code this even in Python or your favorite programming language, okay? You can codify this procedure so that whatever positive semi-definite matrix, Gorini, Kossakowski, Sudarshan matrix I give you, at the end you give me the Kraus operators. Okay, and in fact, I think we have a student here who has this program, okay? So at some point, I'm hoping that we debug it, and then you can all have a Python script that you put your Gorini, Kossakowski, Sudarshan matrix, and it spews out the Kraus operators for you.
Numerically or?
Numerically, because it's in Python. I think we can, if we use SymPy, there might be a way that we can do it symbolically, but then we have to contend with how we have to check whether SymPy, how good is SymPy with doing the matrix exponentiations and these Jordan forms and so on.
Okay. QT probably does have this integrally.
Probably yes. Okay. So this is the procedure. That's all it is. Okay. Obviously, I did it for a qubit. You can do it for a larger system. It gets more complicated, but essentially the procedure is this one. Okay. I should mention one other trick, which is a little bit dirty, that you can play if the Hamiltonian doesn't satisfy this, is you use a Taylor approximation and find your map for small delta t. Because in other words, what you do is you say, well, so this matrix here is this matrix here, right? If I now ask for a very small time, then I'm using the Taylor expansion. I know that this is the identity plus delta t m of L, right? And then I can at least construct my matrix for delta t, and then if I want to go to any larger time, I just apply this map the number of times I want, okay? And that's it. That's all I wanted to say. This concludes everything. I hope that now you are complete experts on quantum channels, and look forward to having you solve some problems for me. Thanks.